Alright, today we're going to look at search strategies about how to go about finding paths in graph. So we're going to find a path from a start node to a goal node in a graph. So at the end of the class we're going to explain how a generic searching algorithm works. We look at both depth first search, we're going to demonstrate how depth first search will work on a graph, how breadth first search will work on a graph, and look at the space and time requirements for depth first and breadth first searches. Okay, so what we're going to do is we're going to find something called a generic search algorithm. So we're given a graph, we're given a set of start nodes and a goal nodes, and we can incrementally explore paths from the start node until we find a goal node. And it's as simple as that. So you're going to maintain what's called a frontier of paths from the start node that have been explored. As the search proceeds, the frontier expands into unexplored nodes until a goal is encountered. And the way we're going to expand the frontier defines a search strategy. We're going to look at a number of different search strategies. So here's the idea. So we have a start node. We have a start node here and a goal node, right? One of the goal nodes here. And we're going to just expand these nodes. We're going to expand nodes. At one stage there is this frontier of nodes that we've expanded. We've searched or explored all these black nodes and all these blue nodes are unexplored. And we're going to stop when we find a goal. So that's the basic idea of what we're doing here. So here's the graph search algorithm. We're going to put as a graph a set of start nodes and this function goal of n that tests if n is a goal. So we're going to start with the frontier is just going to be the set of singleton paths, where s is the start node. And then while the frontier is not empty, so we're going to do this search. So while the frontier is not empty, we're going to remove a path from the frontier. If we found a goal, we're going to return that path because we found a path to the goal. Otherwise, we're just going to expand it for every neighbor. So for every arc from nk to n, we're going to expand this and add that to the frontier, and we're just going to repeat. So what we're going to do is we're going to look at this in Python. So here's my Python code for this. So it's supposed to be just as readable before. It's just like the code before. So we're going to look at while there's not an empty frontier, just like before, we're going to take something off the frontier. We're going to take an element off the frontier. Don't worry about these displays. They're just for printing, and this is just for keeping track of what's going on. If there's a goal, so if the end of the path is a goal, so if that node is a goal node, we're going to display something. We're going to save this solution. We're going to turn the path. So if you just ignore the displaying and the saving things, it's just like the pseudocode before. Otherwise, we're going to find all the neighbors of the end of the path. So at the end of the path, we're going to look at all the neighbors. We're going to display some more stuff. Then we're just going to go through all the arcs. or reverse it for some reason we'll explain later. And then we're going to add all of those, every arc in there. So in the list of neighbors, for all the arcs, we're going to add that to the end of the frontier. Okay, that's what we're going to do. So in the path, we're going to do that. And we're going to keep going. We're going to display a few more things. Okay, this is the Python. The reason we did the Python is as close as possible we could get to this pseudocode that we had before. So have a look at that. And we're going to play with it. You don't need to understand the Python code. We're going to play with it. We only need to understand it when we're going to modify it. So now which value is selected from the frontier defines the search strategy. So which one we're going to choose. And the neighbors define the graph. And the goal defines what's a solution. So, and if there's more than one answer is required, you can continue the search from this return statement. So we can sort of view this as a coroutine where this return, if we can just keep going on and find it. So the Python actually works like that. We can find multiple paths. And often we want any solution, we want the best solution, and the costs and arcs give costs and paths. We want the least cost path. So that's what we're often going to do. But first of all, we're going to look at a very simple algorithm called depth first search. And all that's happening is the frontier is a stack. So always select one of the last elements added to the frontier. So if the list of paths is on the frontier is P1 and P2, P1 is selected. The paths that are expanded to P1 are added to the front of the stack, in front of P2. And P2 is only selected when all the paths from P1 have been explored. So let's have a look at an example of doing this. So if we have this graph, it's going to expand them in this order. It's going to expand. This is one. It's going to do this one first. And let's assume it's going left to right. It's going to add this to the frontier. It's going to, the second one is this. And it's only going to explore this node here where the red dot is after it's explored all paths from 2. So that's dot is on the frontier. Now it's going to expand this node 2, and then it's going to expand this node, and this is on the frontier. Then it's explode this node, 4, and this is on the frontier. Then it's going to do 5, and this is on the frontier. Then it's going to do 6. And then what happens is the frontier, there's nothing left on the frontier, so this is the next node to expand. Okay, then it's going to do 8, 9, then it's going to do 10, 11. Then it's going to go back up to this one as 12. Then it's going to do 13. Okay? 14. So notice how it's going down depth first way. The only thing that matters here is which one it's going to expand. There's 16, 17. It backtracks to the last point it found. 18, 19, 20. And only when it's explored all of this does it then expand this one here, 21. At that stage, the frontier contains these 2 nodes. Okay, so that's what's going to happen here, is it's going to expand these in this order independently of where the goal is. So it's sort of a bit stupid in the sense it doesn't take into account where the goal is when it's doing it. Okay, so here's it in a neater way. After it's expanded node 16 here, this is what's left on the frontier, these red nodes. Okay, so I'm going to give you a quiz during class. I'm going to ask you which of these A, B, C, D, E is depth first. Which of these goals, suppose all of these shaded ones are goals, which ones are going to find first? Just have a look at that and see if you can work it out. And all of this behavior just becomes by treating the frontier as a stack. Alright, here's some questions we're going to ask in class. Does depth first search guarantee to find a path with fewest arcs, or the least cost path? And what happens on infinite graphs or with graphs with cycles, even if there is a solution? What's the time complexity as a function of the length of the path selected? What is the space complexity as a function of the path collected? How much space does it use? And how does the goal affect the search? Okay, so we'll ask these questions in class, have a think about them before we do this. And in breadth first search, we're going to treat the frontier as a queue. So a queue, remember we take it from the front and add it to the end. So it always selects one of the earliest elements added to the queue. So in depth first search does the latest element added to the queue. Breadth first search does one of the earliest elements. So if the list of the frontier is P1 to P3 to PR, P1 selected, and its neighbours are added to the end of the queue after PR, and then P2 is selected next. So it's just treating it as a first in, first out queue, which you should have seen before. Okay, that's breadth first search. Here's how it goes, here's how it works. So we're going to start off, this is the first node expanded, then we're going to expand this one, then we're going to expand this one on the right. Then we're going to go 3, 4, 5, 6, 7. Then we're going to work over here. The frontier now contains all of these nodes here. And it's going to do 8, 9, 10, 11, 12, 13, 14. Let's go to 15. Okay, we're assuming we're expanding from left to right here, just as before. And then what's on the frontier at the moment after we've done this is all of these nodes are on the frontier. Okay, so that's what's going to happen here. So we have this breadth first search, it works here and expands all of these nodes until it finds a solution. Okay, so here's a neater version of this, of showing what's on the orange nodes are on the frontier. It's the same order as before. And now I want you to think about which of these nodes, which of these shaded goal nodes will the breadth first search find first. Okay, so think about that for the class on Tuesday. Now let's look at the complexity. Here's some questions we want to ask. Think about, does breadth first search guarantee to find the path with fewest arcs? So what happens on infinite graphs or on graphs with cycles if there is a solution? What is the time complexity as a function of the length of the path selected? What's the space complexity as a function of the length of the path selected? How does the goal affect the search? Okay, and one other strategy we're going to look at initially is having, when there's costs associated with the arcs, the cost of a path is the sum of the cost of its arcs. So we're going to assume that this cost of n1 to nk is going to be this. It's going to be the sum of the costs of each of the arcs. So an optimal solution is one with minimum cost. And so an obvious algorithm in here is at each stage, lowest cost first search selects a path on the frontier with the lowest cost. And the frontier is a priority queue ordered by path costs. And if you do this, it turns out the first path to a goal is the least cost path to a goal node. And when the arc costs are equal, what do we get? Okay, we're going to talk about this on Tuesday. Thank you.